Hello, everyone, and welcome to the latest issue of Scrubbing the Skies, the webinar series of the Institute for Responsible Carbon Removal at American University. As always, I'm your host, Will Burns, and I serve as co-director of the Institute. One of the most abiding issues for the carbon removal industry, perhaps even more abiding given some of the headwinds that have developed in the United States recently, is how to ensure rapid scaling of an industry that we know needs to be much larger than what is currently projected in terms of current market trends and how we do that in the context of both voluntary carbon markets as well as potentially compliance markets. A second issue that's top of mind for the Institute is the role of the Global South in carbon removal, both in terms of a top line of how we ensure that the interests of the Global South are protected and we do not repeat some of the mistakes that we made in terms of massive scaling of fossil fuels, but also what opportunities might there be for the Global South, who's been disproportionately impacted by climate change, to benefit economically and socially, politically from a scale up of carbon removal in these regions, perhaps benefiting from some of their natural advantages. We now have a new study that is a confluence for those issues. It's entitled Unlocking the Future of Climate Smart Agriculture in the Global South. And this report is commissioned by Stripe Climate and Carbon Gap. And we are fortunate today to have the author of that study, Tom Mills, who serves as a Stripe Climate Fellow and works with the Frontier team on durable carbon removal in agriculture. As always, our format is Tom will start with an initial presentation to hit the high points of this study. And then I will try to seed the conversation with a couple of questions, and then we'll move to audience questions. So in that latter context, I encourage people to start populating the question and answer box throughout, and I will get to as many questions as possible at the end. And so with that, I would like to turn over the microphone to Tom Mills.
Well, thank you very much. It's a great privilege to be here. I've been a big fan of your work, listening to your podcasts for a while, and so it's a great privilege to be here today. I'm going to share my screen, and then we can get stuck into some of the work that we've been engaging with, and I'll explain why I'm saying we as well in a minute. So really, what I wanted to talk about today was that intersection of agriculture and carbon removal. Agriculture really sits at that center of the climate challenge that we are also passionate about, but also at the climate opportunity. And we'll talk about it being responsible for a chunk of global emissions. But I'm really going to focus this discussion around two highly promising carbon removal pathways: biochar carbon removal and enhanced rock weathering. And this study really, or this discussion really builds on this piece of work that we've been engaging in for the past 5 months or so, really assessing 5 key areas: the climate, the agronomy, the environmental, socio-economic, and commercial potential, and also the sort of getting into the nitty-gritty of the science. We reviewed over 240 academic papers, the field trials that have been ongoing, but also the commercial deployments of these technologies around the Global South. The report specifically developed with agribusiness in mind, so those soft commodity traders, the food processors, the consumer packaged goods companies, and we focused on them due to their incentives to make changes within the supply chain, increasing supply chain continuity from climate resilience, decarbonisation, scope 3, but also those who had the finance and also had the contacts with the farmer to change practices. We built this up with around 50 different groups through 5 working group sessions. We had project developers from the Global South working across biochar and enhanced rock weathering. And we also brought in some key think tanks and those looking at these challenges very closely, be it Cascade Climate, RMI, some of the investors and the advisors in the space, but also those groups who are setting the standards for isometric CSI. So the way I'm going to frame today's discussion is in 3 parts. First of all, the agronomic challenge that is being faced in the Global South at the moment, then shifting over to that climatic challenge that we're more familiar with, and also thinking through some of the accounting mechanisms that we've got at our disposal. And then for me, at the center of this really lies that farmer story, that farmer challenge, the ones who are going to be implementing these projects on the ground. So solving any one of these requires tackling all 3. And that's where Biochar and ERW can play a unique role. So I'm going to start by looking at the context of the agronomic environment that we see ourselves in. So soil degradation's among the most critical, but also underaddressed challenges in global agriculture. It's estimated that around 65% of the world's croplands are moderately to severely degraded, and that figure is really profound for productivity, profitability, and climate resilience. It's not evenly distributed. It varies in its severity and its mechanism, but however, there are 3 core degradation pathways or factors that we see. Soil acidification. 1/3 of sub-Saharan Africa is affected by acidic soils. 15% are experiencing very severe acidity. And that means that these low pHs, things like aluminium become soluble, toxic. It inhibits root development, reduces access to nutrients such as phosphorus and magnesium. And so we see these big productivity losses, 10 to 50%, due to acidification. We also see some of the mechanisms for managing that pH in other areas of the world, such as agricultural liming. It's often not economically or logistically feasible in many parts of the Global South, especially in low-value cropping systems or remote geographies. We also see declines in the structure of that soil, loss of soil organic carbon, the physical integrity, and that has a real bearing upon the soil's ability to hold water and to manage these sort of moments of drought as well. And also we see nutrient deficiencies where there's a lack of some key micronutrients in the soil. So these are sort of get compounded. And over the last year, last few years, we've really seen that translate into commercial challenges. So the red in this map here from a study that came out last week, which demonstrates extreme heat, brown droughts, and blue is around floods. And these have all translated into these big price spikes, these supply squeezes, price spikes. And where soil is more degraded, the impact of these extreme weather events upon these global supply chains, be it coffee in Brazil, rising 55%, or be it potatoes in the UK or rice prices in Indonesia, we see these jumps due to extreme weather events, something that's only going to get worse. And agriculture represents quite a paradoxical force in the climate system. It's a significant contributor to emissions, but also one of the most powerful levers that we have for mitigation. It currently accounts for around 22% of total greenhouse gas emissions, but offers around 35% of the world's land-based mitigation potential, more than any other sector outside of energy. But the emissions profile is pretty complicated. It's highly heterogeneous. We have carbon dioxide, the largest contributor, agriculture is the largest contributor to deforestation and land use change. We have waste management challenges around agricultural residues decomposing and then ending up back in the atmosphere. We have fertilizer, which is highly carbon intensive in its production methods. And then we also have methane, where decomposition happens under high water content environments, such as flooded rice paddies, or enteric fermentation within livestock. And also we see nitrous oxide emissions, which is most powerful, one of the most powerful pollutants, 280 times of carbon dioxide, driven by excessive fertilizer application. And then we have soil organic carbon being either a source of emissions or a sink, dependent on the farming practices that we have. So it's one of those few sectors that act as both a potentially high potential carbon removal, but also, if we get it wrong, potentially a source of emissions as well. And then, as I said before, we have the farmer at the center of this challenge. Smallholder farmers, of which around 1 billion people rely on farming for their livelihoods, have quite a challenging time in terms of living income, and are highly exposed to volatile commodity prices like fertilizer. We saw 50% increase and then decrease after the Ukraine war, so they're very exposed to that price. And also we see the next generation of farmers leaving the sector. Not many people are working in. Not many people want to come back and work the land, and this really compounds around 50% of smallholder farmers only achieving around 50% of the potential yield when compared to the high numbers on well-managed estates. So it's a very inefficient mechanism. In some regions of the world, we have this system of increased fertilizer use, increased cost, declining soil health, greater acidity. In other areas of the world, we have under-fertilization as well, and quite non-responsive soils. So we have both ends of the spectrum. So within that context, we see that biochar carbon removal and enhanced rock weathering have this really high potential to respond to these challenges. And this is something that pioneering agribusinesses are starting to embrace and include in their long-term climate strategies. So this is JDE Peat, which is one of the world's largest coffee buyers. This is their net zero strategy. And you can see that biochar makes up this big slice from 2030 onwards about how, in relation to how they are going to achieve net zero. And we're starting to see that with other agribusiness. Ecom Agri's got pilots out at the moment. Vol Cafe's got pilots out as well, and there's more and more interest in this area. And in terms of quantities, we're talking about 13 megatons, 10 megatons by 2040. These are substantial volumes of removals from these practices. And some of those key drivers of why they're looking at them. Firstly, this is a method that does not compete for land use. A number of other activities such as low-till, cover cropping, agroforestry can compete with for land use. There's a low risk of reversal. A lot of net zero pathways are dependent upon soil organic carbon, which has great risk of reversing and being listed as an emission by SBTi. This presents a hedge to that, and also biochar has actually a protective potential on soil organic carbon. It doesn't require a lot of change in farm practices, can go into existing inputs, and also this provides substantial climate resilience, facilitating that sort of supply continuity that's required. And also a big piece of legislation that is of concern is the EU deforestation risk regulation, and also traceability that's required as well. So these are practices that have a substantial potential within the agribusiness ecosystem. And now I'm going to tell you, having sort of given the context, I'll tell you about what they are. I'm sure we're all very aware of what biochar carbon removal is and enhanced rock weathering, but I'll just give a bit of a of an overview. So with biochar carbon removal, biomass residues from agriculture or forestry are collected to serve as that feedstock. And we have a number of different potential ways that they can be processed through pyrolysis. It could be distributed units, be it Kentucky kilns or Kentucky kilns with bells on them to manage methane slip, or they could be hybrid projects where you have a more of an industrial pyrolysis machine on wheels that can go and go to where the biomass is collected, or it could be larger industrial plants. Pyrolysis being heating in the absence of oxygen, and then generating a set of outputs, be it heat and energy from syngas, or it could be a range of products from biochar or bio oil. For example, the really fascinating work that Mashmix is doing into bio oil for the shipping industry, creating a net negative fuel, 2/3 biochar, 1/3 bio oil, blend it with heavy fuel oil, creating net negative energy source, and also generating a removals component as well. But what we're going to be talking about today is applying those outputs as a soil enricher for agriculture. From an ERW perspective, we're taking unused silicate rock powder, so alkaline rock powder, of which there are large quantities, especially in the global south, where I used to live. In India, we have the Deccan traps, the Rajmahal traps, these big igneous provinces, which is then applied on cropland using existing machinery or practices, whether that's however fertilizer is typically applied to the soil. That rock powder reacts with rainwater, CO2 from the atmosphere to generate bicarbonates. It's used to manage pH and a liming capacity, remineralize degraded soils, and reduce that fertilizer component. And we'll talk a bit more about the detail of this. And then is ended up in the river network into the oceans. And from a chemical perspective, we see this basaltic rock reacting with the this is forsterite reacting to create magnesium ions and dissolved silica, ultimately bicarbonates that then end up down into the weather system. It's one of the most stable forms of carbon removal that there is. And the other thing worth mentioning is that there are a range of places that these technologies can occur within the mineral value chain. At the input stage, biochar could be coated on fertilizers or integrated with composts. ERW could be, rock powder could be used to replace ag lime. At the farm level, we see these soil amendments that we've been talking about. At the processor level, we can take this large biomass aggregation and use it as a waste management tool. We see that with sugar bagasse, sugar mills in a variety of different places, or wood chipping factories. So it could operate at the processor level or at the trader level, implementing bio oil into that logistics, and then ultimately for sale as well. Now, one of the things that was really interesting from this research was around the substantial opportunity that the global south, so Latin America, sub-Saharan Africa, parts of Asia, all the way to Southeast Asia, are highly optimized for deployment of these practices. Large biomass residues that exist that have not been optimized. From in the tropics, accelerated weathering from heat, humidity, monsoon rains, lots of water moving, speeding up that weathering process. Lots of abundant underutilized rock, acidic degraded soils, and this real need for agronomic benefits, and also operating synergies with existing agricultural systems. And so we can see this in the lower costs of deploying in, say, India, Indonesia, Mexico, when compared to other areas around the world. That faster weathering rate, that lower cost of doing this activity. And today we see a large portion of projects, or sorry, we see a large number of projects coming from the global south. And then we see this very substantial potential. Some of our modeling suggested that around 25% of the world's estimated durable removal needs by 2050 could come from biochar carbon removal and ERW in the global south. So now turning to that, where that agronomic benefit lies, principally from a biochar perspective, it lies in three areas. Soil structure, which could be improving that physical properties, improving the bulk density of the soil. Biochar is a very spongy addition, creating greater aeration, increasing the availability of plant water content, and also with that, these crevices and these sponges, improving the retention of nutrients, but also in the chemistry as well. Biochar can help manage pHs. It has a natural ability to increase acidic pHs and also enhance the cation exchange capacity, allowing those soils to hold on to and exchange nutrients more effectively, and also enhance microbial activity, so shifting nutrients up and down in the soil column, creating greater aeration. And that really builds out this potential for improved yields, the potential for lower fertilizer use, the potential for drought resistance. And that's really played out within the literature. So this is some of the meta studies that have been done, and there is a robust and growing body of scientific evidence showing that biochar can significantly improve crop yields, particularly in acidic, nutrient depleted or low carbon soils. And when we start to look at deployments throughout the global south, you can start to see that play out within these commercial contexts as well. Whether it's husk ventures producing a fertilizer blend, or biological producing a fertilizer blend in Kenya, or mash makes applying their biochar into the cotton sector or into the coffee sector in Brazil, we see exciting yield potential from these activities. Now, while these yield benefits are very well supported by the research, successful outcomes really depend on how biochar is applied and on managing a few key risks. And this is the same as any agronomic inputs. Biochar is not a one-size-fits-all. If applied incorrectly, performance can be suboptimal or even counterproductive. But there's an increasing understanding of some of these challenges or some of these risks that can be managed, such as soil pH sensitivity. Applying to alkaline soils could raise the pH too high. If biochar is made from low quality or contaminated feedstocks, this could be concentrated within the soils. And one thing which I think is really important, if the biochar is not charged with, say, putting in it with a compost, that the spongy-like properties of biochar may draw in fertilizer or nitrogen into its structure in the first year, which may lead to nitrogen being less available to crops in the short term. And so that needs to be, even though that becomes available in the longer term, it's worth being aware of that potential, but also potential economic, the need for farmers to adopt these practices and to demonstrate the value. And I think here it's really important to note that, unlike other industries, farmers in their lifetime may only have 50, 60 harvests. Therefore, you only have 50 or 60 opportunities to test out new practices. So it really matters. Getting this right really matters. Very, very different to industrial applications where you can test 50 or 60 in a day. So it's worth bearing that in mind when we think about this. From an ERW perspective, we see pH management, improved resilience, nutrient replenishment, all potentially translating or having high potential to translate into yield. And as I said before, often in these areas, access to agricultural land is very challenging. It's unaffordable. There isn't a logistics. So this provides a way to manage that to provide pH management. And really, in terms of the peer-reviewed literature, we're not at the level of meta-studies yet. But I think some of the strongest results that we've seen have come from the global south, where soils are typically more acidic. And in temperate systems, maybe they're a bit more modest, even if they're positive. And also this is translated into results on the ground, whether it's from InPlanet, who sold or delivered the first credits earlier this year, or with Terradot, who's seeing across different commodity types, or in India and Mexico. So we've got quite good geographic spreads. And so we can see this benefit. However, as interest in ERW grows, it's important to acknowledge that while the scientific foundations are solid and they're improving, the number of large-scale geographical diverse field trials remains quite limited. And I think we can be both ambitious but also responsible, with a clear-eyed understanding of there are uncertainties that exist, and there are risks. You know, some of them I've put down here around our understanding of interactions with soil organic carbon, different rock powder variability. Are there risks to soil structures if there's large quantities of rock being put down? Contamination with heavy metals, requiring a lot of testing. If you're applying and lowering pHs, and then you stop applying rock powder, is there an increased aluminium mobilization and also what impacts are there on the ecosystem? So it's worth us being aware of some of these uncertainties, and also as we move forward, working towards to managing them. So now I'm going to just turn to some of the climatic areas, and I think this is, I'll go through this quite quickly, but agricultural decarbonisation in the global south is really critical, but it's really complicated. Food and beverage, around 80 to 99% of their emissions are scope 3, so within their value chain, something they don't have control over. They supply, many consumer packaged goods companies have scope 3 targets. Those targets are typically between 33 and 50% reductions by 2030. But there are these big old structural challenges. One, very fragmented producer network. So you're dealing with what could be thousands, tens of thousands, hundreds of thousands of producers. You may rotate multiple crops over on a single hectareage. You may shift out your sourcing networks on a harvest by harvest basis. Typically, companies may have limited visibility of their supply chain. They may rely on local traders. And also there's quite a challenging lack of standardization around and measuring flag emissions in this area, which we'll talk about in a bit. It also requires a change to farmer behavior, and that farmer behavior varies very, very drastically across regions. I talked a bit about this earlier, so I'm not going to go into a lot of detail, but it's worth just saying that there are many tools that agribusiness could use, and cover cropping, no-till, agroforestry have been, and other regen ag practices such as precision farming have been are tools in the toolkit. And one thing I would say about biochar carbon removal and enhanced rock weathering, these could be very complementary, not competitive practices within a wider regenerative agriculture setup. So just turning to the potential, the climatic potential. So this slide is trying to highlight that biochar and ERW could have meaningful carbon reduction benefits. That's from energy and heat substitution, fertilizer substitution. It could have meaningful nitrous oxide reductions from decreasing the amount of fertilizer that becomes nitrous oxide from the land, and from decreasing the amount of fertilizer that's put on the land. It could be less methane that could be caused by crop burning or anaerobic decomposition. And then we have this durable removal component, and also this biogenic removal, the soil organic carbon component. So there are these different areas that have a climatic impact. And to convert that into a sort of an example, this is a flooded paddy system in India. It's about 14 tons of CO2 equivalent per hectare per year. And we see we could reduce that down between, say, between 1 and 2 tons per hectare per year through reducing the amount of fertilizer required by resulting in nitrous oxide reduction, by the reductions in the methane emissions from anaerobic decomposition due to biochar addition, say, and also this durable removal component from biochar as well, which takes you up to around 9 tons of climatic impact. We haven't looked at SOC in this because it's pretty challenging to measure. So you have all of these potential benefits, and we go into detail in the report on a variety of different scenarios around different contexts. And one thing to note is that there are, this is very, very context dependent. And I'm just going to talk to you very briefly around how to account, because I think this is going to come up in the discussion, or I hope it does. Where the projects are within the value chain will determine whether this is an insetting project or whether this is an offsetting project. And a lot of work has been done on offset so far, carbon market, voluntary carbon market. However, there is this substantial opportunity if that removal or reduction activity happened within the sourcing region of origin or the supply shed, that could be directly related to your scope 3 and not an offset, but an inset. How that looks is quite complicated. So there are shifts between a offsetting accounting mechanism, which is focused on intervention accounting, and the inventory accounting required for a scope 3 SBTI, required by SBTI. There's also a requirement for ongoing monitoring of that inventory. So that would be the amount of removal in the soil, potential for that to become a source if that then decreases over time, and also it to be traceable. So we're seeing this play out from an inventory accounting perspective in terms of the emissions factor. So the emissions factor going from, say, 10 to 7, and then that working up through supply chain inputs. And then for the durable removal component, there are a range of options, and some companies today are thinking about selling them as an offset, or internalizing them, or waiting until the flag guide. And a good example of this, of where insetting has worked very well, is in Klassemann-Delman, which is a sub-state manufacturer in Europe, where they have a client who is an oat bar manufacturer in Germany. They wanted a net zero oat bar. They calculated the emissions per bar with Carbon Future, ran that through the supply chain, through the food processing and back to the field, and then applied the quantity of biochar on those fields that was required to make that a net zero bar. We also have Plan B working a really fascinating project with the Better Cotton Initiative in India, looking at how to implement these insets into the cotton supply chain. And one point I just wanted to mention here is it's something that I think is really interesting. That the prices we see today, one of the reasons I'm so excited about these technologies and these practices is that the prices we see today are not the prices we see tomorrow. Enhanced rock weathering, a large component of that is MRV. And as we understand the open system better, that will reduce substantially down. And also I see these optimizations in biochar carbon removal as well. And then lastly, coming to our third piece of the puzzle, the farmer, all of that agronomic benefit, some of that climate resilience benefit we saw could really translate into climate resilience, interest from the next generation, increased rural jobs. We see in Namibia, PyroCCS, looking at the potential of over 10,000 jobs. In India, we see cotton yields on their smallholder farm plots rivaling top global producers. With multi-carbon, we've seen this big increase in incomes for those who are applying their rock dust. And also something very close to my heart, public health. In those regions of the world where biomass is burnt, this is a really substantial opportunity to pyrolyze that biomass and so it is no longer in the air for children to breathe. So just sort of to summarize, there is this very, very large potential for decarbonization from these practices that combines emissions reduction, emissions avoidance, and durable removal, and could have real dents upon companies' Scope 3 footprints. And really importantly, these climatic benefits are land use compatible. They don't require conversion of land, and they can be integrated into existing agricultural systems. But at the same time, they have this substantial agronomic and environmental opportunity. It has the potential, if done in the right context, using the right practices, knowing enough about the open systems to restore fertility, improve input efficiency, and build climate resilience, while managing that waste and then reducing things like nutrient runoff, which are a big problem in some regions of the world, and generate off the back of those two components this socio-economic benefit, this inclusive development, this allowing farmers to raise incomes, invest more in their practices, increasing the rural jobs, which have been very challenging to create in these areas, but also the fact that there are robust commercial cases for agribusiness to do this, especially where they have declining productivity within their supply chains. There is these substantial co-benefits they can generate. So biochar, carbon removal, and ERW, they're not silver bullets, but they are high potential, high leverage, multi-benefit tools that can align climate mitigation with supply chain resilience and rural development. And I'll leave it there.
All right. Thank you so much for that, Tom. So I'm just going to start off with a couple of questions, and then we'll move to audience questions. And again, I encourage audience members to start populating the Q&A box so I can gauge how much time we should accord to that. One obvious question, right, is you talk about compelling commercial benefits, potentially potential compelling co-benefits for farmers in the global south and so forth. But to date, mostly what we have are extremely small projects and an extremely limited number of projects, right? And we know what a lot of the barriers are, even in things that we've claimed in the past are, clearly beneficial, right? Often don't come to fruition, right? And here we're talking about huge amounts of diffused stakeholders in terms of farmers in the global south, limited information, limited capital, high risk profile, discontinuity between their farms and markets that might be important for this. How do we bring that all together in some reasonable time frame?
A very, very difficult question. But I think at the heart of this challenge is the agribusinesses. I think this is one of the reasons why we went and focused upon the commercial rationale for doing this. Why would anyone invest money to do this? And I think there are some key commercial drivers there. I would say that these large trading houses have substantial linkages to that farmer network and are highly reliant upon that farmer network. So you take the coffee or the cocoa industries. These are industries that are highly, highly susceptible to volatility in supply. Coffee is some of the highest prices per cup at the moment in the coffee value chain. And we're starting to see these pilots getting scaled across the supply chain. So you take Net Zero's project in Brazil across a larger area, an industrial facility, biomass coming towards it. But also we're starting to see innovations around accessing smallholder farmers, but using hybrid or more developed technologies as well. And we've learned some lessons around, well, how can we take these distributed models, either through putting pyrolysis machines on wheels, go to where biomass is, making sure we understand what it is, and having a really, really robust mechanism of processing that waste and making that valuable to both the farmer, but also the agribusiness at the same time. And I think, say, for example, Cortera's tie-up with Volcafe, Cortera's tie-up with Newman, we've got some other very good companies in Colombia, say Biochar and others, working on this. So that's on the biochar side. I think agribusiness has a big role to play, and I believe they are further ahead than in the ERW space. Mm-hmm. And I think companies like Ecom, Agri-Industrials, has some incredible pilots that they look to scale. They're looking to scale up. I think Valley Calibut's looking at this, and a raft of others. And then on the ERW side, I think there is a lot of learning around how to engage with smallholder farmers on these technologies. For example, Multi-Carbon has done an incredible job to work out how to incentivize, how to look at this. And as I said before, you've only got 50 to 60 times opportunities to test this in a lifetime, so it's got to be quite good. And I think once agribusiness comes into that area, I think that's going to be really exciting as well. I think there's some big opportunities there. So my answer to that is really, there has to be a commercial driver to do this. Those commercial drivers are climate resilience, they are scope 3, they are potential to sell in some value chains, to sell a low carbon premium, as we're seeing in coffee, and also to give the CPGs what they want. So that's where I think the opportunity lies.
Okay. All right. Thanks for that. All right. We have plenty of questions, so I'm going to move to those as we have about 18 minutes left. First question from an anonymous attendee. What other soil CDR pathways are you looking at? Have you reviewed biologicals or amendments that build MAOC? I think that's mineral associated organic carbon, right? Correct me if I'm wrong. What are your thoughts on this type of carbon build in soils?
So I've got to declare that I'm not an agronomist and I'm not a geochemist. The sort of, which is, I wished I was, because it's incredibly
me also.
But so we've taken quite a narrow approach on really trying to get to grips with these two technologies. I think what is interesting me today is around the potential combination of biochar with other inputs, be that compost or be that fungi or be that other elements, to then have a different agronomic impact. But I haven't looked into other soil impacts from outside of biochar. I think it's interesting looking at comparisons with no-till, low-till, cover cropping and agroforestry, of which these methods compare very favorably, but also could be a lovely reinforcing cycle. Agroforestry increasing biomass, more biomass for biochar onto agroforestry. There's quite a nice circular potential here for some of those combinations. But no, I'm going to disappoint. I'm afraid I haven't looked at these areas.
Yeah, that's okay. And I think that last point's an important one, is obviously looking for conflicts between potential processes, but also looking for synergisms, right? Because I think there's a lot of them with both biochar and ERW with some of these other approaches. So I agree.
And also potentially together. And I think it's worth just, one of the things I'm getting really excited by, and we had a paper released by a great academic out of Hamburg, Dr. Maria Elena, this week, talking about trying to advance our understanding of combining ERW and biochar on the same hectareage. Mm-hmm. If we're going to have those logistics, if we're going to have the logistics channels, investing in sampling, in MRV, how can we get the maximum removal reductions out of the same hectareage? And I think that's quite an interesting area, and where our science will advance quite quickly, I hope.
Yeah, I think that's right. And I think some of the low-hanging fruit, like cover cropping, for example, in no-till, right, where there's synergisms, it might help drive some of those others into the market more quickly. So it's definitely worth looking at. Okay, next question. This is from Peter Jenkins. I've seen proposals to turn U.S. dairy manure into biochar for application as fertilizer. Do you have thoughts as to that idea and its feasibility?
I think it's worth looking at. Each biochar is all biochar is not the same, and you can optimize around a number of different areas: agronomic benefit, heat benefit, carbon removal benefit, other products. And so, when we're talking about sewage sludge, manure, we've got to be careful about what we're trying to optimize for. And I think in this instance, it's worth being really careful about what is going to be what are you trying to do here, and does it equate to that pathway? I don't know about what the contaminants would be, but I think it's worth just really testing what are you trying to do. If it's just an agronomic benefit, then you just have to test your biochar like any other and check it's in line with what you're trying to get on the land. When I was in India, we were looking at the potential for sewage sludge to be a massive removal method due to the large quantities of unmanaged sewage biomass there, and we sort of worked through the process and we couldn't quite work out how to make it work, but big source of potential biomass there. But I think it will require substantial testing before it goes on the soil for PAHs and other elements.
Great, thank you. Next question from Catherine Webb. Have the communities where these projects have been located been excited about these projects, or are these projects met with skepticism? What community engagement has been done to educate communities and get their feedback, right? So I guess there's two questions there, right? Sentiment of communities and community engagement protocols in the Global South.
So there are different modes of doing this. So there are different ways of doing these types of projects. One is compensating the farmer for their labor, and they get a proportion of the carbon credit revenue. The other is around providing either the biochar or the ERW onto that soils, and maybe a hybrid of the two, so for free. So there has been, like any new agronomic input, there has been, and rightly so, there has been, in some scenarios, there has been skepticism around whether this is the right thing to put on the soil. So I think and that's why there are large-scale trials going on. We're trying to get trials into national agronomic institutes to be able to really show and test and demonstrate to farmers the potential here. But where I can give examples, say in Rwanda, where farmers are so excited about biochar that it is just an input requiring no other revenue. They are no carbon crediting revenue. They are seeing the benefit on the soils. In India, likewise. So once the benefit's seen, then there is an adoption. However, getting to that place of adoption lots of people have been skeptical, as they should be. As I said earlier, you only get 50 or 60 attempts at putting something new on your land. So there is a rightful skepticism, and there needs to be a lot of education to be able to overcome that, as there should.
Okay. Next question from Ashwin Murthy. How does the emissions of mining and transportation of the rock material used in the ERW factor into the emission savings, right? So classic LCA question for ERW.
So so I'm not an LCA specialist either, but my understanding is if the rock dust is a waste and has been come off a waste, then you're looking at the logistics to get it to the site. One thing I find extremely interesting about this is, say you take ION's model, where they're shipping rock powder from Northern Europe to the Mississippi, that the LCA still works due to the very low carbon intensity of the shipping industry, whereas trucking something short distances is very intensive. So, there's this interesting hinterland challenge. I think from an LCA perspective, that trucking is balanced by the fast weathering rate that we're seeing in some of those tropical environments as well. Heat, humidity, monsoon, rain, we see this rapid weathering under those optimal conditions. So there's something to play with there, but this is a waste at the moment, and therefore the mining is not part of the LCA. Who knows what will happen if the industry scales up to a gigaton scale, whether that will be included.
Right. And presumably, if we're going to scale to that, right, we're going to be looking at actual grinding operations. I was just curious if you have any concerns about the impacts of mining operations, especially because, again, they'd be concentrated in at least in the global south in vulnerable areas with limited regulatory oversight often.
So this is an area very close to my heart, Will. So I spent the first half of my career in the mining value chain before then moving over into the agricultural value chain. So the mining industry is fascinating. the industry since the 1940s made a ton of mistakes, and those mistakes were very, very commercially costly around social license to operate, around having red time on those facilities, around not sharing value appropriately. And I think there are some really great lessons that we can learn as an industry from the mining sector. I think also some of those top mining, so very responsible mining companies today have got very, very good at how to deploy and work in these contexts. And it's a real USP. You can't compete on very much else in mining than being able to operate without much than operating with a social license to operate, because your price is fixed. And therefore, this is a real key skill set for these guys. So I think we need to take the lessons learned from the past, take some of those skills that the mining industry's got today, and ensure this isn't an extractive industry, but one that gives the value is shared appropriately. And I think there are some fantastic organizations like the International Council for Metals and Mining that are real experts on this exact subject that I would want to bring into this conversation as well.
Yeah, I find that interesting too when I think about how much this ecosystem has to expand in terms of players if when we start thinking about scaling as opposed to small scale field experiments, right? And the role of those institutions, and it's another ambitious kind of heady sort of challenge, right? To get them excited and galvanized in the process. But I think you're right. Okay, next question is from Reinmar Seidler. Is asking about challenges in distribution or transport of ER materials in mountainous regions, such as smallholder populations. And his example is probably a place near and dear to your heart, the Himalayas.
So we have one area of ERW we have to think about is health and safety as well, and so I think it's worth saying that this is going to, as this develops, health and safety will have to be key. So when we think about movement of rock powder, we're thinking about potential for dust and also the application of that. So that's something to think about. I think that if the LCA works and you are able to transport that rock powder safely, then that should not be a challenge. And I think there are companies such as Alt Carbon who are doing this very, very successfully in the Himalayas, in those mountainous regions with those switchbacks at the moment. So I think, I think it's a manageable logistics challenge if the LCA works.
Right.
Which I think maybe is an interesting question around if you are if you're getting detailed on your LCA and you're going uphill a lot as opposed to on a flat, whether that changes the situation, I don't know. But I'll ask someone who's expert at that.
Yeah, I think that's what the question is going to. And so, yep, yet another thing to consider. Question from Peter Jenkins. Many sources of ERW minerals are places like mine slag and quarry waste with high decontamination costs before it can be safely accepted or applied in ag fields. Roughly at what cost point does it no longer make sense to use ERW from such sources?
Interesting. I'm gonna get back to my sort of consulting days. So the average at the moment we operate in a cost plus basis for credits. So say the average price of carbon removal of ERW credits, $310 a ton, effectively pretty much the global cost. That cost will substantially come down, hopefully over time, as I said, due to the MRV cost. So say a quarter of that is the cost of sourcing and production. A big slice of that is MRV costs. I can't give a definitive answer on that, but I think if you think about it being cost plus 308, 310, massive slice of that is your sampling, your MRV cost, then your sourcing cost is quite small at the moment. So I can provide a sort of a key figure for that. But I think as we have to go beyond wastes, and I think there's lots of low-hanging fruit waste at the moment in terms of quarry waste and others that can be used. We'll have to see, basically.
Yeah. I have a question related to the assumption about bringing costs down of ERW. Obviously, it's quite expensive vis-a-vis some of the uh, alternatives currently in the CDR world, right? And so to have market penetration, as you suggested, ultimately we're probably going to have to bring MRV costs down substantially. I guess I'm a bit skeptical about us being able to do that or do that in a way that has high integrity, right? Because my understanding is ultimately, if you're going to bring the cost down, you can't have these granular site by site sort of analyses of what's happening in terms of exchange and precipitation, things of that nature. But you're going to have to use modeling, right? And there are folks, including at my institution, Northwestern, who are extremely skeptical that modeling ever gets us to the mountaintop in terms of being able to accurately assess the amounts of MRV that we're getting in the quintessential open sort of system, right? What's your thoughts on that? And if we can't, and if we're still highly dependent on site-specific sort of analysis, is it possible ERW is never economically viable?
A great question, and it's really at the heart of the viability of this sector. I think it's worth splitting the question into two. First of all, those sites for year one. So year one, sampling density. Year two, reducing sampling. If we are starting to understand a specific site over time on that specific site, having got to enough statistical rigor, are we able to decrease our sampling density and use a model on those sites? So that's one point. Then for greenfield, can we use a model for something we haven't put rock down on before? So I think those are two slightly different questions. And I think we will get to a place where we will have enough scientific certainty after enough years where we are expanding upon existing sites and we're tweaking, and then we're able to get those sampling densities down substantially because we understand the open systems. And I think over time, I wonder if over time we will start, as we have generated enough field data, we will start to see patterns that we can utilize for those new greenfield sites. And that's something I don't know, but I wonder if that will allow us to get there. And that's for geochemists to decide. But I'm optimistic that the current sampling density, as we understand more about the science, will be able to go down. And I think there's some other people who believe that, and be able to get, maybe not down to zero, but maybe, somewhere along that pathway. And so how much can we use a model for? It's going to get more and more, I suspect. And so therefore the costs could come down.
Okay, great. One last question for you. The site indicates that there is a follow-up report that's coming directed instead of at the business chain, but at policymakers. And I was wondering if you could very briefly indicate what the content of that was and what's your ETA.
So thanks for raising this. We wanted to look at something that would be focused on food security and also on where development institutions, such as development finance institutions, could play a really catalytic role. So using them as the key audience for the report. We hope to have that up in October. There's it'll be slightly tweaked. We'll keep the same sort of structure, agronomy, climate, socio-economic, but instead of having that commercial slice, we'll look at how development institutions and policymakers can be catalytic in this space through whether it's finance, whether it's field trials, whether it's farmer adoption, or it's a number of other areas such as the infrastructure that the market's going to need in terms of laboratories or others. So we're really getting into into trying to think that through at the moment.
Great.
Yeah.
All right, we appreciate that. So once again, Tom, thank you very much for a rich presentation and rich discussion between our audience and yourself. It raises a number of issues, right, that invariably we'll continue to discuss that are really important in this context in terms of both the business case and how to ensure that this is done right. So I really appreciate your time today, and we will be back in approximately a month. We're have a slower schedule in the summer, but please look out for our announcements. And this presentation will be available in about a week on our YouTube channel if you want to share it with others that might have missed it. So thank you very much, everyone, and goodbye now.
Thanks a lot. Cheers.